Okay, so once again, good evening and welcome to the online interactive lecture series, which have been happening now for more than 16 weeks by the INO project. We had varieties of talks encompassing high energy astrophysics and nuclear physics and many other interesting instrumentation talks. Today we have another very interesting and exciting lecture by Professor Nilmani Mathur from Tata Institute, Mumbai. The talk is titled Beautiful, Charming, Exotic Hadrons. And before I even introduce today's speaker, we would like to thank Professor Vivek Datar for proposing this talk and also making sure this talk happens. And of course, we thank definitely Professor Nilmani to agree to give this talk. Nilmani did his bachelor's from Calcutta University and master's from Cambridge, and then he went to Rensselaer to do his PhD. And subsequent to that, he did postdocs at Triumph, that is the Canadian Particle Accelerator Center at University of British Columbia in Canada, University of Kentucky, Jefferson National Lab. And then he joined TIFR, where he's a professor now in the Department of Theoretical Physics. His research interests mainly include high energy particle physics, high performance computational physics. So that's a very interesting combination. I'm sure you will get to hear the developments and also the intricacies about the computational physics as well. I hope during his talk he will emphasize. But he worked extensively on energy spectra of hadrons during the last couple of decades, using some of the biggest supercomputers of the world. So that's what I was meaning to say, including those which he is responsible for setting up and being used in Tata Institute. He predicted a few subatomic particles which were discovered later, and he did first lattice QCD calculation to show the presence of quark orbital angular momenta in Proton, which will now be probed at the EIC experiment at Brookhaven National Lab. So with this very short introduction, I think let us give more time to the speaker. He has quite full presentation to share with you, and sorry, is very inspirational at the same time, very exciting lecture. So first, Nilmani.
Hi, Satya. I'm audible to everybody?
Yeah, perfect.
Okay. Thanks to everybody for coming for listening this talk. And I'm thankful to Satya and Vivek Datar for inviting me to give this talk. So what today I will talk about some of the exciting thing that's going on in the hadronic physics. Title of my talk is Beautiful, Charming, Exotic Hadrons. So we know that I think everybody who are in the audience know what is hadron. And there is some exciting thing going on in the hadronic physics. Some new particles have been discovered during last 17 years. And I will discuss those. So before that, let's start from the beginning. What's a hadrons? And then gradually I will progress to this exotic part. All right. So what's a hadrons? So hadron is a composite particle made of quarks that we know, held together by strong force in a similar way as molecules are held together by the electromagnetic force. That's the Greek, it is a Greek word. It means thick, stout. So this I got from Wiki. Then the first time the name hadron came is in a conference in 1962 by Okun. There he proposed this name and he told that I shall call strongly interacting particles as hadrons and the corresponding decays hadronic. And he guessed that I hope that this terminology will prove to be convenient, and it turns out to be right. Okay, so what hadrons do we know? The first one is proton, of course, that everybody knows. It was discovered by Goldstein in 1886. This H+ hydrogen ion discovered in the anode rays. And the name proton came from Rutherford in Manchester. Proton means first. And he gave this name. And now we know, all of us know that this bombardment of proton gave us the nuclear structure, and that experiment was done by Rutherford. We know the mass of proton very well now, and its mean lifetime is very large, and it's stable. It is the only one stable particle actually among all hadrons, proton and antiproton. And the next one, common one, is the neutron. A neutron was discovered by Chadwick, and he got Nobel for that, and its mass and most of the properties we know very, very well. Then we know Pion. Pion was proposed by Yukawa in 1935, and then Powell discovered it in 1947. Both of them got Nobel Prize. And Powell discovery came from the cosmic ray captured in photographic emulsion. We know very, very well Pion's properties. There is a charged pion, there is a neutral pion. We know their mean lifetime very well. So I'm giving this introduction just to see, just to build up like what we know about hadron and what we don't know. Then the hadrons, there are other type of which are made of strange quarks like the Pion, lambda, omega. So Pion actually was proposed in 1943 and discovered. I got interested to see that in strange particles there is some Indian connection also. The Ashwin Vishwas, I think he was in Melbourne and he discovered he was associated with the discovery of lambda. This strange particle make a big revolution in our understanding of these hadrons. This theory came from Gell-Mann, Nishijima, and Fayas in 1955 to 65, which built up basically the quark model. And the discovery of omega hadron that proposed by Gell-Mann that gave him also the Nobel Prize. So these are various type of hadrons was discovered in last century and till 1970 there are lots of hadrons got discovered, and after that in 1974 the next different type of hadron came, that is the charmed hadrons, they're made of charmed quark. And this is a picture that I obtained, I think, from the wiki also, or some paper, I forgot now. The discovery of charmed hadron actually so-called the November Revolution, because it's a new type of particle came which was not observed earlier. And it was proposed earlier by Glasso and other people. And so discovery is a big thing in particle physics. After that, the next different type of hadron came immediately next year. So that is the bottom type of hadron. And this is upsilon spectrum that I have showed you. The mass of upsilon here is given and the width also. So to see that width, the upsilon and the previous page, these gap psi are very, very small in the keV range. So up to 1975, 1977 actually, all these particles got discovered. Charm, strange, bottom, light quark hadrons, and lots of them got discovered, and particle physics is full of them. Now, this is like a basket full of mesons. There are various types of mesons you can see in the particle data book. And if you go to the particle data book, this is full of particles. I mean, I don't want to read all of these, but just showing you that many, many particles got discovered. This is the quark anti-quark system. And then also the basket full of baryons also. There are lots of baryons got discovered, the 3-quark system. And if you go to the particle data book, there is also, this is a summary table of particle data book. There's a huge number of them, and it is getting added every year. Now, up to 2003, that was the case. So these are the least, some of these particles. But after then, there came something newly found states. Some new hadron came. They are called XYZ. I will tell you why they are called so. So these are the new discovery, new hadron. But what is the big deal about them? That I will gradually tell you what are the big deal about them. So the point is that there are some new type of hadron. I would define what is mean by new. So these got discovered. Okay. Now, before telling you, let me go back and again build up like what is the problem of understanding of this new hadron through our conventional way. So we know that if we build up a periodic table of hadron-like things, so that will basically lead us to the path of the quark model. So many states with various properties that I've shown that light quark, strange quark, heavy quark, the many hadrons that particle data book have found out over the years. So what can we learn from them, and what are the constituents? Let's go back about the periodic table. The periodic table of elements, so that it help us to understand the atomic theory of chemistry. And that we know the atomic spectra that help us to understand the development of quantum mechanics. Similarly, these lots of hadrons helped us to build up a model, quark model, which is a model for these hadrons, and also QCD, which is a fundamental theory of the strong interaction. The various properties of these hadrons help us to build it. So the many regularities, the symmetry of these hadrons was found out among these observed particles. The various multiplets, what I saw next, that can be formed using these symmetry groups. Which is completely mathematical, the symmetry groups, but they actually dictate the properties of this system. And they help us to build a theory by assuming hadrons are composite and made of objects, so-called quarks. So that's Gell-Mann's theory about, Gell-Mann's U theory about quark model. So this is a meson spectrum. If you can put them in certain pattern, and this is the meson octet. The quantum numbers are given like 0 minus, 1 minus minus. These are light quark meson. And it can be, by the SU symmetry group, it can be very much, very well can be described. Some of them is not well described, like the F0 mesons. Basically, the 0 plus mesons difficult to explain through this quark model. But other than that, most of them can be explained very nicely. So there are certain symmetry properties help us to understand these particles. And then also similar thing for the baryon. The baryon octet I showed you here, baryon octet in the decuplet with some strangeness. And basically, even now, many of them can be described very nicely and quite accurately also. There are some problems. So state of quark, even D-bar like type of meson. They came out with a paper, which is, I think every of you have seen sometimes, the schematic model of baryons and mesons. Like the meson, also found the baryons at bound state of 3 quarks. The quark concept was supported experimentally later by deep inelastic scattering, the Rutherford type experiment at SLAC first. And Friedman, Kendall, Taylor, they got Nobel Prize in 1990 for these experiments. And the quark dynamics, the strong interaction dynamics, understood later through quantum mechanics, quantum chromodynamics. And Gross, Wilczek, Pollinger, they got Nobel Prize 2004 on that. So with that, I will just so that is a model for the quarks. Model for the hadrons, the quark model. And with that, now I will jump to QCD, and so that there are some problems with these models, and then gradually we'll build up for the exotic hadrons. Now, for QCD, that I will just little bit brief introduction that we have these quarks. These quarks are UD up, down, jump, stem, top, bottom. These 6 quarks and they're anti-quarks, and these are the masses is put there. And the theory of strong interaction in quantum, that is quantum chromodynamics, it tells us that quarks are the fundamental constituent of hadronic matter, and they have 6 different flavors: that up, down, strength, charm, bottom, and top. And also, it tells us that quarks interact via by emitting and absorbing massless particles called gluons. So the new concept came is gluons, which is not in the quark model. As a fundamental way, maybe in an effective way, but not in a fundamental way. The quarks and gluons are endowed with 3 color charges, and there is self-interaction between quarks, which is not present in the electromagnetism. And one can write down a simple Lagrangian, which is written here, but it is extremely complicated to solve, and actually analytically it is not possible to solve so far. So because of the strong interactions, the quarks and gluons are confined within the hadrons, and so they are not observed in nature. So the QCD is telling us why don't we see quarks outside? We just see the hadrons because the quarks and gluons are confined inside it. And if we know how to deal with strong interaction dynamics, then we will be able to see the properties of these hadrons. The hadrons are color neutral. So this is like a snapshot, like some experiment is going on, like the SS bar meson, and then it is breaking up to different type of mesons. So if you want to break them, it will not be broken. It will be go to the different type of 2 different mesons. Similarity, you can take the analogy like to magnet. It's not exactly the same thing, but just the analogy. If you want to break the North Pole, the South Pole, you will not be able to do it. So similarly, when a high energy collision, you will get not quarks but these hadrons. I made a little bit cartoon. Let's say these are 2 cars colliding. Let's say proton. If the 2 cars collide, we know what will happen. They will just break. But here, in high energy collision, what happened? The more cars actually came out. So 2 BMW colliding, and lots of other cars are coming out. See, if it was in the real picture, that would have been nice. All right, so this is a picture, a typical picture of the high energy collision when 2 particles collides. Then this is a jet picture. A huge number of particles came out at the end, and these particles, of course, are the hadron. And by studying these properties of these jet, we can find it out the reactions, how it's going on. All right. Now, these force between the quarks become weak for small quark separation, a phenomenon which is known as the asymptotic freedom. That means in very, very high energy, it is small. And if you go on the low energy, coupling is very, very large. So that's the main problem, because then we'll not be able to solve it. So our all knowledge of mathematical knowledge is that we can do some perturbation theory, and from there we can build up the theory. But if the coupling is very large, we cannot do perturbation. So you bring to me the next transparency. So what generally we do? So we write down a Hamiltonian and expand it in terms of some perturbation of some coupling constant, which should be small. If the coupling constant is large, then you cannot do this perturbation. Here the coupling constant is something like this. At high energy, it is very large, so you can do calculation. You can write down the Feynman diagram, but at the low energy, like if you want to know the properties of proton at low energy, you will not like the mass of the particle, mass of proton, or the form factor of proton, then you will not be able to write down these Feynman diagrams because the coupling is very, very large. How do you know the coupling is large? Of course, experimentally, but this is a typical, just little bit analogy. Like if you mass of hydrogen atom, if you summed up proton and electron mass and little bit binding energy, that's basically the hydrogen atom mass. And so if you want to get, you can do this perturbation theory, there's no problem, and we know it is extremely successful. But on the other hand, if you add up the masses of quarks, it is just a 2% of the whole mass, and most of the mass is coming from this strong interaction. That means coupling is huge. So you cannot do any perturbation theory. So a composite hadron, that the Gell-Mann picture in the left side is made of quarks, 3 quarks only, UUD. but actually the actual picture in the right, so proton and neutron looks like this. There are jillions of up-down quarks, anti-quarks, gluons are there. And what do we mean by the made of 3 quarks? Here meaning is that there are this infinite number of them are there, but if you summed up all of them, at the end, you will get these 3 U quarks. At a given time, there will be 3 U quarks, and it's a 2 U quark and 1 D quark for the proton, and other are basically cancelling out in the sense of counting. And this is a complicated picture. So it is very similar to like the valence picture of the atomic physics. Like there is a valence electron in an atom outside, and that dictates the properties of the atom. Basically, how much interaction will happen, it will dictate by this valence electron. Similarly, this valence, these leftover, after the total counting, the leftover at a given time, these 3 quarks, they will determine the properties of this proton or any hadron. So that's the meaning of these valence quarks in terms of the QCDs. Now you can think about these like all this proton, neutron in terms of the QCD, something like this way also. If you think that there is a creation operator, this cello is like the vacuum, and all these particles will be nodes of these. Then you can think about that. This is a vibration of the QCD vacuum. Okay. Now let's go to start the talk. So this is just the introduction. Let's go to start the talk now. So study of hadrons, it is a connection between nuclear and high energy physics. So we can study the energy spectra and then build up models that I showed you. The energy spectra helped Gell-Mann to build up this quark model, which is very effective. Then now these exotic multi-quarks, multi-hadron hypernuclei, there's lots of things are coming out, and that gives more information about the strong interaction. And we can get the structure of these particles, like the form factor, spin, orbital, angular momentum, GPDs, TMDs, by studying the hadronic physics also, by studying these hadrons, which help us to understand more comprehensively the strong interaction. And also in hadronic physics involved in hadronic matter, at finite temperature and density. At finite temperature, there is something different happen, and I'm not going to discuss that, but it's a very, very important part of the hadronic physics also. All right. Now, what do we know actually about these QCD like potential? Like I told you that the 3 valence quarks are there. Now they must be interacting somehow. And what is the interaction? How the interaction looks like? And I showed you the asymptotic freedom also, like at large distance, there is, you will not be able to separate out quarks. So here is a picture of 2 quarks and their interaction by the flux tube. So in lattice QCD, actually, it is possible to calculate these interaction and the strength of interaction. And here is that means the potential. Here is a plot of the potential. From the actual data, it showed that there is a linear part at the large distance, and then there is a Coulomb part. So you can write down the potential according to that, and then you can write down a model on that. So your potential will be a linear part, it will be a Coulomb part, and then you add up other parts like the hyperfine splitting, the spin orbit splitting. Similar to quantum mechanics. So once you have Hamiltonian is known, then you can build up a model. That's basically the quark model way what Gell-Mann proposed. And now we know what could be these from the lattice calculation. We can actually figure it out what type of strength we should put for a particular hadron. Now, as I was telling, the potential can be described like kinetic part, this HK, this is in a constituent quark model. These right side, you can see the V, as I was telling, the V is a Coulomb part, then a linear part, and then some other parts are there. And that's why the Hamiltonian is written like this way. SD is the spin orbit, some part, and so basically you can write down the Hamiltonian in a nice way, and then you solve the problem exactly as in quantum mechanics. and it turns out to be very, very effective. So here a picture of the potential and different spin states it just put there. This is for the Quarkonia picture, CC bar and BB bar picture. It shows that by taking a particular type of potential, you will be able to describe the CC bar, BB bar spectrum extremely well. Even in some cases in MeV range, it's so accurate where the mass of the bottom is 10 GeV. So here is some sample result from a quark model calculation. This is just one quark model calculation. The experimental result is shown at the right side, and theory coming from these is on the left side. You can see how accurate can it be by taking some appropriate potential in a consistent way. So basically, it is showing that we can describe through a potential way the CC bar, BB bar, with Charmonian spectra very well. So that was that. So far, so good. So that means we understood what's going on. It is basically two objects. If we know the potential, we can calculate it. But so this is the energy spectra of Quarkonia. What I showed the result earlier. Like basically, it is plotted. This figure, this table is plotted there. The energy spectra, CC bar, BB bar. We can well describe it. That was then, but what is now? Now is this. Just look carefully. There, let's go back again to the previous one. The CC bar, BB bar states are there. Now I put many other states on top of that figure. These states came recently. There are so established pre-2000. The blue one is pre-2000. The other colors one are after 2003, basically. It's after 2003. So there are many states got discovered starting from 2003, which basically does not fit into this table, into this table, and that means into this model. It does not fit. So these states we cannot describe by taking a potential and calculate its mass, calculate like quantum mechanical way. So that means something funny going on. We don't understand this QCD. QCD cannot be described by that simple type of potential. It is basically telling if these particles are real, so that means we don't understand. So this is like charmonium, bottomonium spectrum that we know today. It is a huge mess. Lots of particles got discovered recently, which does not fit this quark, anti-quark, this type of potential Gell-Mann way of describing it. It does not fit. So actually, this is CERN itself from 2012. It discovered 37 new hadrons. Not all of them are these this type of particles, but most of them. They discovered 37 new hadrons. So they're discovering actually a lot of them now. As you can see, 2020 they already got many of them, and we think there are many will come. Actually from lattice calculation and also the models, we predicted many of them, and they're coming regularly and almost at the predicted range. So this is exciting time. That's why now this is the newest addition of on that list. It just came last 2 months. The first one is on the top. The first one is on the invariant mass spectrum of JEPSI in PP collision. It shows 2 new particles came out. One new particle came out, 6900 MeV mass, and they called it X. I will tell you what by that mean. This particle cannot be described through a quark model like a CC bar spectrum. It inherently had like 2 C quark and 2 anti-C quark. 2 charm and 2 anti-charm quarks, because it's a particle is JEPSI, and it has like 4 quark structure, which is not in the quark model. And just last week, there is another particle came, B plus to D plus D minus K plus decays, and it's basically D minus K type of. Earlier, it should have been like D plus D minus. That's but now it is coming D minus K channel also. So that means it has a C bar D U S bar structure. The 4-quark structure manifestly is there. And the signal is pretty large, 5 sigma, that is what in the bottom that I'm showing it. So it just came last week. So there's many these type of particles are coming, and they cannot be described through these quark model. Which some cases it in 10 GeV it is 1 MeV error bar, so which is very successful, but couldn't do anything for this type of particle. So these are the exotic. Actually, there are many more predicted. Last year, actually, we predicted some of the other particles, which is type of 4-quark state, but made of made of 2 same quark, like BB, and 2 other quarks, like say UB, US, UC, something like that. Here, what I plotted the binding energy as a function of these x-axis are these particles, and y-axis is the binding energy, and you can see some of these binding energy huge, like near 200 MeV. These will be deeply bound. Of course, these will be discovered later because it has 2 p quark. You need very high energy to produce those. But at some point of time, we are sure that this will be discovered. And not only we, many other people are also got into this business. So that means many are coming. This type of particle will come, and it will not be possible to describe them through this regular quark model. But beyond the quark model, there are other things you can do also. I mean, as a quark model also, you can do just tweaking a little bit. A constituent picture of hadrons can be described because QCD had quarks and gluons. We know that in quark model, gluons are not there. So if you put the SU3, the color charges of the 2 quarks, it can be 1 + 8. We know the one that came out as a 1 + 8 that came as a meson. And if you put 3 of them, there's a baryon. But you can do the color charges 8 × 8. So that will give you the blue ball. And then you can build up 2 quarks and 1 gluon inside, like 3 × 8 × 3. So that will give you the hybrid. I will discuss later what type of particles are these. So if you just include the gluons inside it, then you will be able to describe some of the state probably, the blue balls and hybrids. But the problem is that QCD does not always respect these constituent leveling. They can mix together. So there will be a mess, and maybe we will watching that mess. The lots of them are there, and it is not possible to describe in a simple way. So the question is, does nature permit what QCD allows? Like I told you, there could be blue ball, there could be hybrid, and there, if I put 4 quarks, there will be 4-quark state. If I put 5-quark state. So they're all things QCD allows. As long as their color singlet, there is no color charges left over as a hadron, this should be allowed in a consistent way. So does nature permit those? What we are seeing that is that all those. Are there subatomic particles beyond mesons and baryons? So that's the main question. Are there subatomic particles beyond mesons and baryons? All right. What are these newly found states? Are these, if they are not mesons and baryons, so what are those? So they don't fit the regular quark model, which is very successful in some cases, but is not able to describe at all these states. So are these then beyond mesons and baryons? All right, actually Gell-Mann on that paper itself, this is the abstract of the paper. You see the red points, so red lines. So he mentioned that 5 quarks, also the 4 quarks, the Q bar and Q bar states. So these are also possibly present that he already mentioned in that paper. Jaffe next in 77, he also mentioned about these 4 quark states. And he tried to describe like this F0 type of meson. I told you earlier the F0 and some of these A0 state cannot be described properly by this regular quark model. So Jaffe at that time came out that maybe it is possible to describe as a 4 quark states. So the concept is already there. Now, do you know actually any multi-quark state manifestly? Yes. What about deuteron? So deuteron is a dibaryon made of a proton and neutron. You can think about a molecule. So we know the deuteron exists, and deuteron, we know the importance of the deuteron. The deuteron had not formed, all neutrons would not have, all neutrons would have decayed. If neutron had not formed, helium would not have formed, and so other elements, and so know us. And the universe as we know it would not be possible. So deuteron is there, so that means it is possible to form these multi-quark states. And so that brings me to this multi-quark business. So is deuteron the only ground state of 6-quark system? Is there other dibaryons? Can multi-quark states beside meson and baryon can be formed? What about in early universe or in extreme condition like in neutron star, pulsar, strange quark star, strange star? Is it possible to bring this multi-quark state there? Can they change the dynamics? And existence of these states can tell us much more about strong interaction. If we can find out these states and find out their dynamics, we'll be able to learn a lot about these multi-quark states. So that's why the study of multi-quark now became very, very important. So let's go back where our basic things. These new states has been found out. The right side picture is showing the unpredicted discovered states. Magenta things are showing unpredicted discovered state. And the people now they're calling them an exotic. So I will now define what do you mean by exotic. What are excuse me, what type of exotic particle you can expect, you can discover, and what could be their properties. So what are the exotic hadrons? The hadrons that do not fit into the naive quark model picture of mesons and baryons, you can tell them as an exotic. Excuse me. So hadrons that do not fit into the naive quark model picture of mesons and baryons, you can tell them as an exotic. Why are they interesting? They provide opportunities to study novel phenomena of particle physics, like the tetraquark state, pentaquark state, hybrid mesons, molecules, hydroquarkonia. I will discuss all of them individually. So you will come to know why, what are they. So these states will help us to understand strong interaction at multiple scales. Like if some system is made of C, S, double C, S, double C, EUD. So like at multiple type of scales, these quarks are, they operate in different scales. So multiple scales, strong interaction could be a little bit different. So we can figure out what are these dynamics at multiple scales, the properties of these particles. How many have been discovered so far? The 0 before 2003, basically. I mean, I'm forgetting about deuteron, but 0 before 2003, but many after that. I showed you CERN that only from some that picture, 37 of them discovered. Why are they called XYZ? Mostly historical reason. Now there is a pattern, like Z are basically electrically charged and isospin 1. Y are like 1 minus minus, met directly in E plus A minus, and X, whatever is left over. But however, there are exceptions about this simple rule. PTG is yet to come with a convention with that, and I think they will come soon with the convention. And for a recent review of the exotic, I'm giving the reference. So those who want to know much about it, you can read this review. So now I define what is the exotic means here. I will define it more. So exotic hadrons, the hadrons whose quantum numbers, actually there are two types of exotics. One, you can think about the flavor type of exotic. One is the spin exotics, and some are crypto-exotics. The hadrons whose quantum number require a valence quark content beyond QQ bar, like this type of meson baryon, they call me exotic. Hadrons whose spin parity and charge conjugation are forbidden in the non-relativistic type quark model, they're called the spin exotic. I will give you an example. And there are crypto-exotics like mass, which does not fit with meson or baryon spectra. There's overpopulation in your spectra. Production or decay properties is totally incompatible with standard meson baryon. You can call them some crypto-exotic. But basically, the first two, the flavor type, there are lots of flavor quarks, and the other one are the more than QQ bar or QQQ, that one type. Another is spin exotic. I'll show you what is spin exotics. So let's say you want to build a meson with two quarks. So The two quarks are given in the two different color. On the right side also, you can see you can form S equal to from 2 S equal to half state, S equal to 0 and S equal to 1. And the angular momentum could be 0, 1, 2. Now total angular momentum is L plus S. So, and parity, we know that minus 1 to the power L plus 1, charge conjugation minus 1 to the power L plus S. So if we combine them, two quarks can form only this JPC allowed these quantum numbers, like 0 minus plus, 0 plus plus, all these. But what about others? There are many other quantum number can be possible. It's like JPC 1 minus plus, 0 plus minus, 0 minus minus. They are possible, but we don't see them at all. So these are particles called exotics. So these particles, if you discover a particle with these quantum numbers like 1 minus plus, so that will be an exotic. Actually, there is a history of 1 minus plus. I particularly emphasizing this 1 minus plus because there is a history of that in PNL. I think 1998 or some year they came out with the discovery. They claim that there is a discovery of 1 minus plus particle. It came even in the New York Times, but I think it's not been confirmed. Jefferson Lab basically trying to get the new version of the Jefferson Lab. They're trying to get this particle 1 minus plus. So these, why this is exotic? If you put a knife quark model like this type of J equal to L plus S, this type of, cannot build that state. Those who are familiar with how to build an operator for a particle, you can see that so here it is 1 minus plus is written as Q bar gamma. Gamma is an operator which can create, like what I was showing earlier, this cello. From the cello we can pluck it and get from the vacuum these quantum numbers. So this gamma is that cello. So you put that Q bar Q, you can create this from the vacuum. You hit it with this quantum number. If you hit this with this operator, you will get this quantum number. Now, no one can show that just between Q bar and Q by putting what type of operator, you cannot get this 1 minus plus state. So you have to put manifestly the chromomagnetic field together. Like you have to put a D operator, the gluon operator between them. Otherwise, you will not be able to create it. So these like a hybrid state. So you have to manifestly put a quantum number, manifestly put an operator which it will be coming from gluon. So this is an example of the hybrid state. Okay, so now, physicists have discovered a lot of subatomic particles beyond the meson and baryons configuration. It looks like that a lot of them I showed you. What are the valence quark structure? Are they, what type of valence quark structure? I defined what we mean by valence quark structure. So the extra, when you summed up, naive way, when you summed up, what are the particle quarks will be left over, and that will dictate the properties. So here is today's idea. Like it is an elephant. The particle got discovered. Lots of people are telling lots of theories are coming. Somebody said this is a cartoon picture that all of you probably know. An elephant, and when you are blind, you cannot see it. You just touch it and see what is there. It could be a wall. Somebody's telling it's a rope. It's a tree. Our situation is something like that. There are lots of models, and we don't know what actually is the structure. Maybe all of them are wrong. Maybe combinedly, all of them they could be right. So that's why I put this analogy. All right. So like this ZC type particle, people are telling this could be a molecule. I will define what mean a molecule. It could be tetra quark. I will define it also, but it is not clear yet what are these particles. So these exotic hadrons, so they could be pentaquark, like the dibaryon. This could be tetra quark. This could be meson molecule. This could be blue ball. This could be hybrid. So these new particles that got discovered, they could be in some of these. So by studying these properties, we'll be able to know how a pentaquark dynamics should happen, how a tetraquark dynamics should happen, how is a hybrid dynamic. So that's why these particles are important, and we will be able to know a lot of things about strong interaction. So now I'm defining what is a tetraquark. So a tetraquark, a 4-quark state containing diquarks, a quark and a diquarks, a quark-quark pair, or anti-diquarks. So an anti-diquark, I will tell you what is mean by that. So diquark model is something like that. So when you multiply two color charges, 3, so 3 cross 3, it can give you 3 C bar or 6. The quarks are strongly correlated by, it can be color spin interaction, flavor spin interaction. The diquarks are not color singlet. They're actually not color singlet, 3 C bar. So they are boson-like object, like spin 0. It could be other spin also, but boson-like object. So this is basically a diquark picture given by Jaffe and Wilczek. So you first build up from 2 quarks or 2 anti-quarks, a diquark or anti-diquarks, and then gradually build up a potential between them. And then you write down a quark model with this quark model type model with these diquarks, and then see and whether you find out you can explain these states or not. So a diquark, a 4-quark containing a 4-quark state containing diquarks and anti-diquarks basically. So a pair of quarks, anti-quarks, can be either in 3 bar 3 or 6 bar. The color SU3 group. So one gluon exchange is attractive in the 3 bar. Found out, I mean, if you do a little bit calculation, one gluon exchange, you can see the 3 bar is more attractive than, and 6 is repulsive. So we build a model with 3 bar. So usually it is found that the spin 0 diquark are more tightly bound. So this is a cartoon picture of the quark anti-diquark, diquark anti-diquark potential. And this is a radius of RQ, as a big Q, small q, is the radius of diquark and the radius of this particle here, R4Q. This model actually is quite successful. These are the references, and lots of other people are working on the diquark, putting a different type of potential, changing this R cube. So this is a cartoon picture, not cartoon, the actual picture of some calculation of the example spectra of diquark, and they can explain some of these new states. One prime candidate for diquark is ZC4430, which is a charged state. And this is manifestly charged. It shows that if it is charged, CC bar is a chargeless state, but if it's a charged state with made up charm quarks, 2 charm quarks, so that means there is 4 quark states are present there. So the ZC is a prime candidate for tetraquarks. But one problem of this tetraquark model is that they produce lots of other states. So if there is a 1 plus state, there will be 1 minus state. There are lots of states produced, but experimentally we don't see so many states. Some of them we see, but experimentally we don't so many states are predicted by the diquark. So then the molecules. What is molecule? Here's a cartoon picture of molecule. The hadronic molecules are compound states of 2 hadrons. So unlike diquark, where the color, there is no color singlet, like this is a meson which doesn't have color. Diquark combination has color, but here 2 molecule basically is like a deuteron. It is a generalization of the nuclei of system of mesons. Basically, it is a generalization of the nuclei of systems of mesons. Like deuterons, they can attract some pion exchange or something, and they can build a bound state. The constituents must be sufficiently long-living to allow a molecular state to form. Like if I want to make a molecular state, the individual states should be also the long-living. They have a particular decay pattern. From there, one can actually figure out the particle you are getting. If you have a complete decay pattern, maybe it is possible to find out what is the structure of that particle, whether there is a molecule or not. One good criteria is that the Weinberg criterion for a bound molecule, which Weinberg came out for deuteron, actually, he showed that deuteron is bound by showing some formulation. These equation shows that it is possible. The lambda basically will show you lambda equal to 1, that is there is no bound of that. G0 is the coupling, G0 mu square actually actual coupling, G0 is the bare coupling. So this is the Weinberg model of deuteron in 1965 came out. So using that, people are now coming out to understand this molecular picture. And these are some of these references. And they came out that particularly these X3872, these particle may be particularly a molecular state, decay pattern shows something like that. We know that if it's a molecule, it is bound clearly, if it is a combined state, it is SOM. And these 3872 very close to the threshold is showing that maybe a SOM molecular state. Some of the other states may be also molecule. There are lots of paper actually came out on that to explain some of these new states. So this is the definition of molecule. Next is the hadroquarkonia. So what is hadroquarkonia? It has a core. The Q cube are core at the center. There's a heavy quark core at the center, and two light quarks are light clouds are outside. So this is some type of picture. The Q cube are core there, and the cloud of light quarks are outside basically. So it's a compact quarkonium core surrounded by an excited light quark cloud. The core and the cloud are held together by the QCD analog of the van der Waals type of force. The decay, the compact core simply stays intact while the light quark just decays down. And you can write down the Hamiltonian in terms of the polarizability. The alpha is the polarizability of magnetic field. So people have the model. These are lots of models are there, so they can explain some of the states. So this is the hadroquarkonia. And then the hybrid. I already talked about this 1 minus plus state hybrid. So hybrid can be explained quite interestingly. I showed you this picture also earlier. From lattice calculation, we have seen the static potential. There's a peak at the position of the quarks, and then you can think about a flux tube. And now one of the flux is excited. So that means gluons are coming manifestly. So that's basically a hybrid state of this meson. So two quarks are there in the hybrid. There is a gluon, excited gluon coming manifestly. So I told you earlier that for 1 minus plus, you are putting these. You cannot get this 1 minus plus quantum number unless you put a chromomagnetic field in between them, so that gluon is there. So gluons bring a new type of excitation to the confined system, so that you can get many other quantum number. So there are some models, and some of the new states are explained by these hybrid state, particularly Y state, some Y4260, that state people are telling maybe hybrid. Then the blue balls. I think you know very well about the blue ball. The story of blue ball is long-standing. The SU3 spectra of blue ball, what I'm showing it here, the x-axis is the different quantum number of blue ball, and y-axis these different blue balls with the quantum number that I showed you. So what is a blue ball? The blue ball is a purely gluonic bound state. In the theory of QCD blue ball self-coupling, showed you the QCD has self-coupling, and that can make a state, that is blue bound state, the color octet. Color singlet state. The 8x8 can give a color singlet also. What is the experimental status? So no conclusive experimental evidence of blue ball as yet, though F0 states at light quark sector are indicative. But the light quark sector main problem is that the blue ball quantum number can have the meson quantum number and also 4 quark quantum number. So they mix together. So you don't know what you are discovering, whether it's a blue ball or a meson or a 4 quark. So it's a mess. But heavy quark, there is a chance actually. So these plot actually, I am also involved in that. This is in the PDG, current PDG, 2006 actually, it is in the PDG. It's a very well cited paper. So we predicted the SU3 spectra of these. And some of the states at the which is 4 to 5 MeV, 4 to 5 GeV region are actually has exotic quantum number like these 1 minus plus type. So it is 0 plus minus 2 plus minus. So if they can be produced, so then they will not be mixed with meson or 4 quark state. So maybe it is possible to discover them easily than the light quark. So Panda experiment basically will look for these type of oddball, they call oddball type of blue ball states, which is exotic quantum number blue ball. Maybe some of these states discovered later will be this type of blue ball. Okay, now I told you these are new states are either 4 quarks, there are molecule or these hybrid, hadroquarkonia, lots of models are coming. But some experimentalists or theorists also are telling there may not be those states. They could be just a threshold. There's experimental effects, the threshold scattering or scarce effect. Some of them, not all of them, some of them could be like that. So here is a discussion on that. These effects mainly arise due to complex analytic features of the amplitude like poles, branch points, Riemann sheets. So here, okay, the simple example is the opening of on-cell channel creates branch point via imaginary part of the amplitude, which by Cauchy's theorem creates a scarce and which can resemble in a resonance. So here the imaginary part of real part has been put, and if you just discover these red points, that may not be a resonance. Basically it could be an experimental effect, and there is a rescattering effect also. And some of the physicists are telling that some of these states are basically the rescattering. Is a threshold effect. Because of this type of triangular singularity is mimicking as a resonance, and rescattering diagrams can create poles either below or above thresholds. So what you are observing may not be a real particle, but it is just the experimental effect. Some of them, but not all of them. Okay. So here I come back to the model again. So model for XYZ states. So we know that these are exciting discovery. They're the compacted type quarks. There are molecules like neutron, there are the hybrids, the hadroprotonium, there are blue balls, and there could be simply experimental effects. And the experimental, if the experimental papers are like this, the theory paper are like this. There are a huge number of theory papers coming every day to explain these states. All right. So now, okay, the 4-quark state exists. I showed you that 4-quark state exists, a quark or molecule. How about 5-quark states? Here is that, the Pentagon Strikeback. Why did I tell Strikeback? Because in 2003, actually, Pentagon discovery was reported, but that turns out to be wrong. In 2015, in lambda b decay, CERN came out that lambda b generally decays depth psi lambda star, but it can come out with a resonance structure with a new particle they call PC, which can have a 5-quark structure, a 5-quark component. And this is the different events count in 2015, and it showed actually more than 10 sigma some cases result, and this is their value. They came out. The mass of the particle, there are two of them. One is 4380, with one width is very small compared to strong interaction. So this scale, this is very, very small, and that came out at 12 sigma. And the other one, 9 sigma. This is a very good signal. And I will show later that all the checks they have done, this is an established particle. It should have a 5-quark component. And last year they came out again the same result, with more statistics. So lambda b decay to depth psi pk decays. The pentaquark structure is something like that. C bar manifestly 5 quarks should be there. Depth psi p, C bar EUD type. They gave the name PC. These are the masses. So these are the masses given here, mass width. So last year they came out. They put 3 structure here, 3 pentaquark structure. 2 are close by. So in order to get the lowest chi-square, you have to put these 3 different particles, and they're very close to the threshold. The threshold is sigma c d0. The 2 thresholds can be possible, and their proximity very close to the threshold. Though there's 2 different observations. One is one of them has a very small width, and they're close to threshold. So this is quite interesting. So what is the structure? The structure could be again like a tightly bound pentaquark made of diquarks type of things that they make 2 diquark, a meson, and then one quark, the potential of 2 diquarks, and then build a model. So it's a tightly bound pentaquark model, or it could be like the molecular type of the loosely bound pentaquark model, or it could be simply these kinematic effects, the triangle diagram cusp that I was talking. What are these? I think it's not clear which one is correct, but as I was telling, that the width is very small and it is near the threshold is like a deuteron type of states. So near threshold masses with narrow widths favor molecular meson baryon type of structure of this particle, species. All right. So now, okay, 4 and 5 quark state exist. How about 6 quark states? We already know the example of deuteron. Is deuteron the only dibaryon state? Let me come back, go back again to Jaffe in 1976. He proposed an H dibaryon made of 2 lambdas. So structure UDS, UDS. So if it has to be bound, then it should not decay to proton. So the threshold should be 2 proton, and the mass should be below, just below it. If it exists, then it will not decay. It will be extremely stable, and so people thought this could be also a dark matter, a standard model dark matter candidate. But recently, some people came out that that may not be true. It may be, may not be possible, because then oxygen would not exist. Some people came out that explanation. What about experimental status? Experimental status actually is that does not exist clearly. We don't see a clear signal for H dibaryon as yet, if it exists at all. The experiment as latest as last year, like the gamma, upsilon decays in 90% confidence levels, they showed it does not exist. There are other experiments earlier also, so it does not exist. But some interesting experiment came out 2013. One new particle, Disturb 2380, and Pion decay, Pion goes to D5050. They found out a resonance structure. And again, there is a small width and this mass. Is it a deuteron excited states, Pion type of bound state? So quark structure should be UDTGU. Actually, there are not repeated experiment on this, but it came out with PRL. Maybe this test exists and more experiment need to be done to establish it. But people came out with the theory that this again can be a dark matter candidate. One can form a Bose-Einstein condensate out of this 6 quark state. But even if these states exist in the condensate, of course, it cannot be a Bose-Einstein condensate, because the radiation at that time will just disintegrate. This mass is so high, it will just disintegrate this particle. So it cannot be a dark matter particle. Okay. Is there any other dibaryon? So we did some lattice experiment with that. So let's say this is a deuteron. Deuteron has UD, UDD. Now, lattice, we can actually change the quark mass easily. So what we did, we instead of putting UD, we change U to C and D to B. So we make a like BBC, BCC, this type of particle. If I call this is a DOD as a deuteron, and DBC is this new particle. Then we change the B to U to B and D to S also. So this is like a DBS, BBS, BSS. We also change to U to C and D to S. So they all are spin one particle. And so DCS, the CCS and CSS. And then we try to see, okay, let's see, if this is bound, what about these? And surprisingly, we found out, so okay, so this is this particle structure, 2 particle structure will be like this. If it is NP state, so this is omega CCB, omega CBB, this will be omega B, omega BBB, and this will be omega C, omega CCC. So we surprisingly found out, so let's say this is a threshold 0 level, and there are states below it. So that means they are actually deeply bound states. Some of them have very large binding energy. We don't know why and how the dynamics it, but this is a lattice observation. We published in PRL, and it's very deeply bound states, some of these. Hoping that some days this will be discovered, but it must be far away, because 2 baryon, proton baryon produced, actually 4, which is large energy. But let's say someday maybe it will be discovered. But it has a large binding energy, so that's interesting. All right. So now, what are the theories to explain all these? The models, as I told you, that the potential models with a diquark molecule, hydroquarkinia, flux tube, many other models. There could be, one can use QCD sum rule. One could use the effective field theory, and then people like us use lattice QCD. So this is just one slide for latticity. So what we do, we discretize space and time, and then calculate the quark propagator. When we have the information of quark propagator, we can calculate 2-point function, and from 2-point function we can calculate the mass, and from 3-point function we can possible to calculate the form factors. And people have demonstrated that these two can go very, very well. This is some cartoon picture how the coordination function looks like as a function of time, Euclidean time. So actually, by performing this lattice calculation for this particle can help a lot of things, because we can get the mass spectra, and if we can able to calculate the form factors, so that will settle the questions: what are the structures? Experimentally, to measure the form factors will be very difficult, but you need the form factor to discern the structure of these particles. We know how much we get information about the form factor, the structure of proton. So if you want to know whether it's a molecule, whether it's a tetraquark, something, we need to calculate this form factor, and lattice can help us. But unfortunately, for this type of calculation, because of the heavy quark component is involved, which needs small discretization error, the computer time is extremely large. So you need a petaflop type computing facility. So that's why it's slowly coming. Maybe in next 5 years it will be more. All right. So how do you check? This is just for some student that actually I was taking a quantum mechanical course last semester, and I gave some of these things earlier. The new particle got discovered. How do you know this is a new state is found? Whether it's a resonance particle or bound state? How do you find out? So for them, actually made these few slides, and I will just strictly go over it. So when a new particle got discovered, what the experimentalist does. Again, this is particularly for the student, not for the expert. So need to check the enhancements in differential cross section. You need to see the 90-degree change in phase shift. You need to see Dulles plot. You need to see Argon diagram. So I will slowly goes over these, and some student maybe will be interested to learn about this. So what is a Dulles plot? So Dulles plot is a scatter plot of mass combination in a 3-body decay to decipher non-uniformity in invariant scattering amplitudes. This is Dulles picture. He died in 2006. So one actually look for the correlation of masses between decay products. So let's say this is decaying to 3 different particles. So what you put the invariant mass spectrum in 2 axes, M12 and M23, and then find out some pattern. So this is a real picture for different F0 particle in pi scattering. You can see some of these correlations are there, and each of them actually are related to presence of a particle. So Dulles come out is a very nice idea, and it is extensively used to find out the resonance structure of a particle, of a discovery. Then this is from the Sakurai's quantum mechanics book. You look for the Argon diagram. So you know that you have to look for this 90-degree phase shift. That is also not sufficient. Let's find out the so what you put in an x and y axis, the real and imaginary part of this phase shift, and see whether it's going like a circle. If it goes like that, then the discovery is happening. And you can see what is mean by this pole structure. You need to find a pole. What do you mean by pole structure? These quantum mechanics book on Sakurai chapter 7 has it. Very good description of that. So student can learn from there what are all these and why the experimentalists actually struggle to do this thing. And once they have done, they're very successful at establishing the resonance structure of the particle. Here is a picture for that. For Z4430, the ZC4430, the first thing, okay, you see a large count. You see some type of resonance structure. This is a Dulles plot. You see some type of correlation. So 2 criteria has been met. Of course, you see the 90-degree phase shift like this, and then this is the Argon diagram. So these all checks have been done for this particle. That's why people trust this. Some discovery has happened. So unless we do all these states, it could be just a scattering state, 2-particle scattering state. It may not be a resonance state. If you want to establish a particle discovery or not, so you have to do all these tasks. This is a pentaquark, the Argon diagram, this is Dulles plot for pentaquark. The clear correlation here and here. So this shows that the presence of this resonance structure is there. Of course, you have to do the other tests also. So here, the Argon diagram of that, and they have clearly showed it, and that's why they could conclude. All right, so this is the new discovery that last week came with LSCB talk. There's a correlation. They showed these axes and these axes also. These axes, this correlation, they claim that's a structure of this C bar D US bar in that particle. So through all these, you can establish whether the particle has been found out or not. All right. So there are lots of experiments going on for this hadronic physics. As I told CERN, these LHCb, Atlas, CMS, they're producing lots of particles. There are blue X experiment that is going on. So I told you that one man square. So one of the major goal is one man square discovery of the blue X. They look for that, and then BS at China. Then Panda experiment that will happen later. Then Bell 2, that experiment will happen later. Compass also is doing, and the other previous experiments are related to that. So there are lots of experimental facilities are trying to get these hadron spectroscopy, and they're discovering new states. So we will very much look for the Bell 2 experiment, and maybe many new states will come out through that experiments. So that bring the end. Here I'm concluding. So many subatomic particles have been discovered in the last 17 years beyond the meson and baryon valence quark structures. Many more will be discovered. The lattice predicted, there are lots of models predicted, and some of the states were discovered later or predicted earlier. So we can think about that. What is prediction people have made? Maybe it will come also later. Some of them at least will come. So many more will be discovered, and need to understand them actually thoroughly, which will help us to understand the strong interaction of our nature. So as I was telling, that if we can understand what's the dynamics for a molecule, what's the dynamics for the hadron harmonia, these tetra quarks, then we'll be able to understand strong interaction much better way. So it is an exciting time to go beyond mesons and baryons, multi-quark states. They may be important in some other places, like I told you, maybe in the neutron star, maybe in the early universe, I don't know. So join and contribute to theory and experiments. Okay, so with that I will end, and I will take questions.
Thank you very much, Nilmani. Really took us from very basics of the hadronic physics, went on, and now bringing up this exciting thing beyond mesons and baryons, as you say, and the multi-quark physics, as well as the experiments and the exciting things that it has ramifications in other areas. So without taking more of the time for the discussion, I would like now to ask people to start questions, post their questions. We already have quite a few. Let us start going in that order. First, Vivek Datar has a question or comment.
Can you hear me, Nilmani?
Yeah, clearly. Yeah,
okay.
Please tell me.
Okay. So my question is related to this question of petabyte requirement for computing these, states. Now, what is the status of quantum computers in this area? I mean, how is it possible to do the simplest one calculations at least with quantum computers, or do we have to wait probably for some big advances in quantum computation?
Well, how to formulate QCD in quantum computer is not known yet. Quantum computer can do some simple problem, but not for QCD yet. So we have to figure out the algorithm for QCD for quantum computer. And some people are trying, some groups to make some algorithm, but so far I will tell nothing, and it will take some time, because how to put this complicated system in quantum computer, we don't know.
Okay, thank you.
Okay, we take next question from Shailesh Pinja.
Hello, am I audible?
Yeah, hi.
Yeah.
Yeah.
Sir, I have a couple of questions from the earlier part of your talk.
Sure.
One of them is like the gluon is massless, similar to the photons for electromagnetic interaction. So when we start building the theory, we may assume that these interactions could be infinitely ranged like the electromagnetic interactions. So what additional constraints are present in theory which for strong interaction which limit the range of these interactions?
So it is not infinite range. Remember, there is a Coulomb part 1 over r, that is, but there is linear part also. So if you want to stretch it, at some point there will be break in the gluonic force. That's called string breaking. So that's why all hadrons are confined. So you cannot build one quark to infinity, another quark to other infinity, and then build a hadron out of that. So the interaction is totally different than electromagnetic interaction.
So I have the related second question. We according to like the asymptotic freedom at shorter distances, the potential should approach zero. So do we really need Coulomb term for those scales? I mean, why is there a Coulomb term in the potentials?
Is a core. So at very, very small distance, so of course this is blow up, but you don't go to very small distance to, so you can actually from the lattice calculus and you can show how far you can go to put this Coulomb term. And for baryon and meson, like they, two quarks are not put on the same position at one time. So there is a linear distance between them, and this is extremely small, of course, in the Fermi scale, but there is a distance between them.
Okay. So I mean, we can't do it with just the linear term, with the coefficient of that linear term being variable.
As you see, this quark model actually, by putting this term, it is extremely successful. So you need that term. But that's a model. I mean, that's a model.
Thank you. Thank you.
If you want to do that type of model, you have to put Coulomb term. Yeah.
Okay.
We take a couple of questions from YouTube before again coming back to Zoom. Abhinav Chaudhary, why quarks do not exist isolated in nature and always bound together to form hadrons?
Okay, that's the properties of the interaction. We don't know, and that's the properties of the interaction, and that is a fundamental force, and we know as it is. Basically, strong interaction behaves like that.
Another one from Pawan Sharma, how we know the forbidden particle according to quark model other than spin exotic particle?
Sorry, what is it?
It says how we know the forbidden particle according to quark model other than spin exotic particle.
So forbidden particle are not only spin exotic, they could be the 4 quark state. The 4 quark state, so quark model has only 2 quark, the quark and anti-quark, and 3 quarks. So the basic quark model are with that. Now you can make an extension of the quark model like this tetra quark model, that's molecular model. These are basically extension of the quark model, but these are in the original quark model. So in original quark model, only Q, Q bar, and these Q state. So these are, so if you have a Q bar state, like 5 quark or 6 quark or 5 quark, 6 quark or 4 quark. So that means this is not considered in the original quark model. So that's why they are called the exotic. So of course there are spin exotics, but spin exotics and these number of extra quarks. So these are 2 different type of exotics.
Another one, is it possible to find a combination of quarks that are not completely color neutral?
No. So then you have to find out a single quark, and as you know, the single quark is not possible to find out. because of this confinement structure of strong interaction. And the color structure is a diquark, that maybe you are meaning that the diquark is, has a color, but in experimentally we don't see any diquark. We only see the hadrons.
A question from Ariom. Ariom, can you ask the question yourself?
Hello, sir.
Yeah.
Please go ahead.
Yeah, sir, like this diquark and this triquarks like Pion and Proton, these are colorless.
No, diquarks are not colorless. Diquarks are colored state. Remember, diquark is formed like in SU3 group, 3 cross 3, like it is a 3-bar color, 3 or 3 bar, but 3 and 3 bar, both of them are colored state. They're not colorless state like Pion.
But Pion
So
is a diquark, like quark and antiquark, right?
Quark and antiquark, that is not diquark. Diquark is made of 2 quarks. Pion is made of quarks and antiquark. So diquark is made of quark and quark, or antiquark. So 2 are same.
Okay. Okay, sir, like this tetra quarks and this pentaquarks, maybe the combination of quarks and antiquarks, is it possible that this are the colorless, or like is there some chance of color?
Of course, they're hadrons, so they're colorless. Otherwise, they wouldn't have been observed. Pentaquark, tetraquark, they're hadrons, so their experimentally has been detected. So experimental detection means, of course, they're the colorless object.
Okay, thank you, sir.
Okay. There is also a question from Rohit. Please ask question yourself.
Good evening, sir, and thank you so much for this beautiful talk. So my first question is that, as you have said that as we calculate the mass spectra of different baryonic states, so why we can't calculate mass spectra of these exotic states from the linear plus Coulomb potential?
You can calculate it, but it doesn't match. I mean, how do you calculate it? So that's a tetraquark. You have to build up a tetraquark or molecular model. No? So if there is 4 quarks, you want to make a quark model. How do you do it?
By diquark, or anti-diquark kind of things.
So that's a tetraquark model, basically.
Yeah. So we can use it.
Yeah. People have done it, and there are lots of can be explained through that.
Yeah. So, sir, how this model is different? Like it is same for other non-exotic states and exotic states. So the model is same. Like what is the difference?
No, the potentials are different. Potentials are completely different.
Okay. And sir, my second question is how glue balls structures are just purely a combination of quarks, purely combination of gluons. So are there any quarks present?
Of course, the quarks and antiquarks are always there. The glue ball does not mean the plot I have shown you. So that's an SU3 plot. That's a pure glue ball. But in nature, there cannot exist a pure gluon. Of course, the quarks are there. The quarks are let's say when a gluon-gluon interaction is coming, the quarks can make a loop, and their quarks and antiquarks can pop up and they vanish. I mean, but quarks and antiquarks are always there. So that is why it is very difficult to discover them also, because they will make up, they will decay to many mesons also. Which is made of quarks and antiquarks. So that's why it's very difficult to discover them.
Yes, and my last question again. You have seen that their spin parity and charge conjugation formula is different from other conventional baryons and mesons. So, am I right?
Some of them, yeah. Spin exotics are different. Yeah, spin exotics are different.
Okay, so generally we can't say that formula that we use to find parity and charge conjugation for other conventional, we can use for that formula for exotics also. Can we use?
Yeah. So let's say if you have 4 quark states,
yeah,
you can use that formula. But if you have a gluonic excitation in between them, then you cannot use that formula. You have to put these. You can use that formula, but you have to put the gluonic excitations. Their spin part, their angular momentum part. That formula is correct. That formula is always correct. But you have to put the degrees of freedom correctly. The problem was that if you put only 2 quarks, then we cannot get these quantum number. But as let's say I put a gluon, that brings a new degrees of freedom. So once it brings a new degrees of freedom, you can put a new L, extra L. So that extra L will add up and then can get these forbidden states. But those formulas are correct. Only it is not correct if you put 2 quarks.
Yeah, in the diquarks it will be different, like -1⁻L only.
Yeah, you have to figure out individually how the angular momentum are coming, what could be the angular momentum between them. The spin, of course, you know, and if you combine them together, that's why in this diquark or hybrid model, people can explain angular momentum of these states.
Okay. Thank you so much. Thank you so much.
No problem.
I thought Amol had either a question or remark. Amol?
Hi, Amol.
Sometime earlier.
Hi, Amol.
Hi. So suppose for a 4 quark state, it is shown that it can be explained very well by a molecule of. Does it lose its status as being called a tetraquark, or does it still stay a tetraquark?
Well, so molecule has this particular way, like 2 mesons are interacting through some potential, some pion exchange or some. But tetraquarks are different. Tetraquarks are 2 colored object, and then you put a potential between them, and they're interacting, and through that you will get it. Now, your question is, can I call a molecule as a tetraquark? So the definition of tetraquark is different than the molecule. So I will not call that as a tetraquark, because the way you build up is different.
Because recently there's a lot of back and forth about whether certain tetraquarks or molecules.
Yeah, so I think the reason is that you build up, let's say, both tetraquark and molecule, and now both of them can get the mass spectrum by 2. Problem is that you tweak your potential and then try to match whether it is matching the mass spectrum or not. Now, by both way you got and you claim that, okay, I explain it. So that's why the controversy is coming. Now, how do you figure it out whether this is tetraquark or this is like molecule? So one criteria, as I was telling, these Weinberg criteria, so it has to be very close to the, so you have to see decay properties. It has to be very close to the threshold. It is narrow, so then it is molecule like, and there are not many states like, if you find a charge state, there is no, so let's say you find a 1+ state, there will be a 1- state. You don't find a 1- state. But the tetraquark says that if you 1+ state, there has to be 1- state. And if you don't find this 1- state, then you tell, okay, tetraquark, what you are claiming is not right. I think all these are controversial and everybody claims they are right. The only way to distinguish them, if you can calculate the wave function. If you can, so decay properties will help to understand a little bit, but if you can calculate their form factors, so I think that will settle. But as you know, these are rare events, so calculating form factor will need lots of statistics. Maybe someday some people will do that. And that's why I was telling that if lattice people can do this form factor calculation, that will settle this problem. Without form factor, it will be difficult. You can infer something from the decay properties, but I think the controversy will still be there unless you calculate the form factors.
Yeah, I think we have just one last question from Ashutosh. I guess, can you ask yourself, Ashutosh? Ashutosh Das? Yeah, please go ahead.
Sir, you showed us that it's this JEPSI, you showed a lot of states are present there, but mostly we saw that most of the exotic are made of heavy quarks. Why is it that?
Yeah, okay, so that's an interesting question. Actually, light quark is a mess. The problem is that there are many states, and there are lots of mixing in light quark because the dynamics actually quite different in light quark. The lambda QCT comes into effect very clearly there. The states like F0 will claim they are the molecular state, like F0980, A0980, they are the molecular state. But problem is that, and Jaffe's model, this tetraquark model can explain their mass spectrum, like the energy spectrum. But the problem is that how to establish those, like whether there is a, and the experiment in light quark does not see so many states which cannot be explained. There are some states are there, and quark model cannot explain these states. And some of the 4-quark model can explain these states. And then there is the F0 state, which people tell that it could be exotic, like the blue ball. Some of them could be blue ball, particularly F0 1500 something that could be blue ball. And also the scalar meson, they could be also some type of this 4-quark exotic. So, but they mixed up so much, they're mixing there so much that it is difficult to establish that. There is one particular exotic, which is 1 minus plus, I was telling. The 1 minus plus, people are looking for it for a long time. And as I told, in 1997 and 98, BNL came out that they have discovered it. But I don't think that has been established. Then Compass also came out that 1 minus plus they have got it. So the pi is particle called the pi 1400, and there is I think pi 1600 also. The Blue X experiment at Jefferson Lab, they are particularly looking for that. But the problem is that they have too many decay channels. There are too many decay channels from this 1 minus plus. So unless you clearly understand all those decay channels and do a good couple channel analysis, you will not be able to establish that's an exotic. But on the heavy quark, that is not the case. There are not so many openings are there. So that's why people are able to discover more in this heavy quark sector.
Sir, by mixing,
does that answer your question?
Just one question, that by mixing you mean mixing between light and heavy, or I didn't understand by mixing?
No, mixing between different states. Like let's say F0 state. So F0 state, it decay to various other states near around with the same quantum number, and then the lots of pion will come out at the end and with the same quantum numbers. You don't know what you are actually measuring.
Okay.
So unless you do a good couple channel analysis consisting all the decay channels, it's difficult to establish. So that's why in the light quark also blue ball is not possible to find a discovery yet. So there is a blue ball. Now it will mix with 2 meson state. It will mix with 4 meson states, and it will mix with many other meson states together. If there is tetraquark, it will mix with tetraquark. So you don't know what percentage of blue ball, what percentage. So in your signal, what percentage of blue ball, what percentage of meson, what percent of tetraquark. Unless you do a good couple channel analysis, you will not be able to establish it. So that is the problem in light quark. Does that answer your question?
Yeah.
Okay. I said that is the last question, but we have just one more hand just raised here. Jahid Ansari, can you please quickly ask your question?
Yeah. Can you hear me?
Yeah, speak a little louder, please.
Yeah. So my question is that I think you have mentioned that due to some observation, there is some conflict in this QCT model, right? I mean, you mentioned that whether nature allow QCT or not. for some observations. So my question is that in that case, if there is some conflict between theory and experimental value of the QCD, so do people find that in those observations, asymptotic freedom is also violated?
Sorry, I didn't tell that there is a conflict between QCD and QCD and the observation. I didn't tell that. I told that so QCD predict those things. So does this thing exist? And turns out some of them exist clearly. There is actually no conflict with QCD.
Okay. I was confusing that part, that how.
No. Sorry that I didn't make it clear. Yeah. QCD predict lots of states, and now whether nature has those, we don't know. And it turns out that many of them are there.
Okay. So, Nilmani.
Yeah. Satya.
Yeah.
I have a comment. Can I speak?
Oh, sorry. Yes, Rajaji.
Yeah, I have written it. I have a simple comment. One of the first hadronic molecular hadrons, which was identified, was lambda 1405. This was in 1967. There are 2 or 3 papers of mine, and I had given a criterion, and it satisfied the criterion in terms of the geometry. So it's actually now established that lambda 1405 is not a 3-quark state, but it is a bound state of hadronic molecules, namely K bar and N, nucleon and K bar. And recently a QCD study, independent QCD study, confirmed this. I just wanted to mention this. This is one of the earliest hadronic molecules. Apart from Weinberg's deuteron in particle physics, this is actually the first hadronic molecule which was established in 67, as early as 67, soon after quark model came. I just wanted to mention this.
Yeah, I'm sorry that I didn't know your model. This lambda 1405 has a lot of controversy. There are many models claim that's a 3-quark state, many models claims that's a KN pentaquark state, and there are molecule state. And the lattice QCD came out, some of these things, and the conflicting, I don't think this is established that it's a molecule or pentaquark or 3-quark state. And there are lattice QCD calculation. I'm very aware. I also did some calculation earlier. The lattice QCD calculation from Japan, some of them are telling that's a pentaquark state. But the problem you have to understand, again, this is like an experiment. Once, when you want to establish this is a 3-quark, 5-quark, or whatever quark number, you first have to calculate what percentage of that. Is there a mixing between them? Is there a mixing between 5-quark state to 3-quark state? Because they could be same quantum number. Unless you show this mixing clearly, then it is as it is uncertain. So nobody has able to clearly establish whether this is a 3-quark, 4-quark, or 5-quark state. Sorry, 3-quark, 5-quark states.
Yeah, my 1967 work is independent of these controversies. In fact, I established the criterion in terms of the K matrix. So if the K matrix has a pole, then it can be a 3-quark bound state. If K matrix,
theory fine, but experiment how do you prove it? Experiment you have to prove it.
No, I showed that the K matrix, experimental K matrix in the 2-channel system, experimental K matrix established that there is no hole in K matrix, and hence it cannot be a 3-quark bound state. That was my 1967 argument. I still stand by that argument. It is independent of any model. It is a model independent criterion based on empirical criterion, namely K matrix is experimentally determined. Just to plot it and see whether it has a pole. It does not have a pole. It is as simple as that.
Okay.
Okay. So that is, I think, gone into a more technical discussion now with 2 experts. But also, I mean, more than that, you already spent 45 minutes or a little more than half an hour in the discussion. So once again, Nilmani, on behalf of all of us, especially the participants, would like to thank for this very, very nice talk, and also taking up this long discussion and question answers. So thank you very much, and
Thanks a lot to you and those who are as the audience. Thanks a lot for staying so long. Thank you very much.
Also
Thanks
asking
from the audience
questions.
side.
Yeah.
Thanks from the audience side.
Thanks.
Yeah.
So I think the
Thank
questions are also so nice that it brought out much more than what you have already presented. So thanks again to participants as well. So just before I say bye to all of you, we have next talk that lined up on Wednesday evening at 6 p.m. By the way, I'm sorry for this confusion about the Zoom link because of these just interviews, I couldn't get the same Zoom link. So we had to use a different one today. But from next talk, again, we'll go back to the same Zoom link which we have been using all this time. So this talk will be by Dr. Prof. Mohanty, going to speak on the CREPS 3 experiments and the exciting results that they have published recently. So with that, once again, thank all of you and say good night and take care and stay safe. Bye-bye.
you and best of luck for next time. Thank you.
Thank you.